So this is the food calorimetry pack for junior science. So I'm just grabbing 10 mils of water. So that's the mass that we're going to increase in temperature. So we're going to use a formula Q equals mc delta T, and the M is the mass of the water. So I'm just filling that up to 10 mils, and I'm going to put that in a boiling tube. So a boiling tube is just a thick test tube that doesn't break because the glass is thicker. So pouring that into the test tube. And then I'll put a thermometer in there and make sure the temperature is stable, and hopefully you do that fresh each time, and it's 25 degrees, and hopefully it starts at about 25 each time. And so that uh, is set up just like that on the retort stand, just finger tightness on that. Now I don't, what I do is I actually try and get about 0.25, 0.5, like going up in 0.25's masses of the chisel. Um, and then I'm just reading that there. And then attach it to the stopper. And I didn't read the method properly. It actually then wants you to measure the mass of the stopper and the food before, and the mass of the stopper and the food after. And I didn't do it that way. And you can do it that way if you want, although the whole class has to decide because the whole class is doing it the same way. Because you need that to get enough data. Okay, so anyway, so I do it, and I did the calculations that way as well, but it's quite easy to adjust if you do it the proper way. I don't mind which way you do it, to be honest. And so I'm trying to just get, because we're going up in increments of five, I try and get approximately around 0.25. So I'm trying to guess, and I just break it up in pieces until I get smaller and smaller pieces until I get something that's close. So that's zero point 0.7, and my first increment's 0.25, and I'm going up in 0.25s. And so what's that? 0.23, I think I sit on. And that's the mass I use. Now I'm assuming all of that gets burnt. Um, and then the other assumption is all the heat goes into the water. It doesn't heat up the glass or anything else, and doesn't just disappear up the sides. So quite massive assumptions. Um, and so the other thing is that's assuming complete combustion as well. So incomplete combustion means it's not all the carbon is combined to oxygen to O2, and you don't get enough as much energy. So even if it is all the energy is going into the water in the test tube, that's also assuming it's burnt cleanly. And as you can see, I thought it burnt, but around the other side it hadn't. And the fact that it's gone black as well, as you can see, with iron that goes black, it actually gets heavier, not lighter, that substance, because oxygen is combining to the carbon. So it's not just incomplete combustion, it's like soot or not even burnt at all or partially burnt. So they're all huge issues. Um, and the temperature can keep going up after it's finished. And all during that time, it's cooling down as well. So there's heat. It's constantly cooling down even while it's heating up. So heat's being lost even when the water is heating up. So that one sort of went up to 32 and sort of stayed there for a while. So I took that as my reading. So 25 to 32, and I wrote that up. If you really want to know, you should read half the smallest increment. So you should decide if it's 32.0 or 32.5 or 31.5, but I think that's smack on the 32.0, but we're not doing uncertainties for this lab. Okay, and then I'm just going to show you the material. As you can see, I haven't really fully burnt the whole thing, so I haven't really finished. So I need to go keep going on that and relight it up. It really should disappear theoretically. Okay, ideally you do this before you do the experiment. And so this is quite a complicated table. Um, so just go through it slowly as I go through it. Just stop and go back as you need to. Um, so we're going to do a range of 5, and we're doing a repetition of 3. Ideally, more repetitions are better. So repetition of um, 0.5 is better. Now, I'm just going to center everything, the entire Excel table. Now I did the method slightly differently, where I didn't take the mass before and after. So I'm not going to change that. Um, Now I've got trial one. And so I've definitely got the water temperature in degrees Celsius. So we insert the symbol, grab that thing, and that we have before and after. So we got that before, got that after, and then we want the change, which is the delta symbol, capital D, delta change. And we don't really want it to take up too much room. So I'm going to squish these. All right. Um, Now I don't know how much room this is going to take up, but I'll just going to start doing some tidying up now, just so we can make sense of some things. So I'm going to merge that, wrap it, and I might just wrap everything. Um, so that's trial one. I've got the water temperature before and after. I'll merge that. And this is the one thing I did do differently. I didn't take the mass before and after. So for this one, I used 0.23. It's the only one I did. And I assumed that the entire thing burnt, which is an error, obviously. I'll just merge that. And that's for trial one. Okay, now it was 25 degrees before. It was 32 after. Um, and so that's sort of how we want it to look. All right, so they're the three trials I want. Hopefully that will work. Yay. That is useful. All right. Um, and then we want to get to the averages. So we'll do the averages for both the water temperature. So that's the change in water temperature. So average, so that's change in water temperature. So that little delta, Control C. And merge that. That looks messy. And average change in mass, the average mass, sorry. Um, the average mass, the average change in water temperature. Um, then after that, we want to know Q equals MC delta T. Um, and then the final calculation, which is energy, and that'll be kilojoules per gram. And the answer, according to the packet, is 22.5 kilojoules per gram. All right, so I'll just merge those. Where's the merge button going? There. All right, now they're titles, they're headings. I'll just clean that up. And I'll just clean that up to make it bold it to make it a little bit clearer. I don't know if I can do anything else to make it smaller. So I'll cut and paste this as landscape on the A4, not as portrait. And that's it there. So I don't have data for the rest of it. So the average water temperature is going to be an average. So we just click on average. And that is not correct. We just want, if I just highlight that, put nothing in there at the moment. I'll just delete that. So I want the average of the water temperature change. So that's this one, and hold the control button, and this one, and this one. Just Control C and drag that down. And averages of the mass equals average. I just put the button in there, and I hold down the control button. So I hold down the control button, and I want this, this, and this done. Okay, so press Control C and then drag that down. Now this is going to be this, so just write equals this minus, and click on that. And press Control C and drag that down. Press Control C, Control V, Control C, drag it down. Control C, Control V, Control C, drag it down. All right, so that's a third of what it's meant to be. So this is all going to be 3 times more than what it should be over here. And hopefully it'll burn it better too, so you'll get a much greater temperature change. All right, so that's a little whack. So play around with those and just get similar number of decimal places. What is this temperature? We'll give it 1 decimal place. And so Q equals MC delta T. So this equals the mass. So the mass was 10 grams of water. And it's 4.18. So it takes 4.18 joules to raise 1 gram of water 1 degree Celsius. And times it's that little star. And so that's Q equals MC delta T. So there's the mass is 10. The C, specific heat of water is 4.18. And the delta T is this, which is should be a lot more than that. It's 3 times more because we did an average and we got zeros in there. So I'll just adjust that to 1 decimal place. And that's per gram. And it's also in kilojoules, the answer. So we're going to divide that by 1,000. And so we're going to grab that and then divide that by the mass. And so just give that 1 decimal spot will be fine. So just check that calculation. So Q is 97 divided by 0.23. And that'll give us our joules per gram, and we're changing it to kilojoules per gram. All right, and so we've got 0.4, and the answer should be 22.5. You got to realize that you'll burn that better, and you might want to change this. It'll be a lot more complicated to get the true mass, and all of those numbers might get you up, to 20%, rather than a massive, much bigger error. This is like you're only getting like 4% or something, a couple of percent of the energy you meant. You might be able to get it up to 20, which is not too bad actually. All right, considering all the errors in this experiment, which are quite enormous. All right, so I'm just going to put some dummy numbers in here. I'm just going to assume that the other masses are perfect, just to get our graph drawn in preparation. So we can just put the numbers in as we go. And then the temperature changes. We start at 25 each time. And let's just say they go up in tens. All right. So, oops, and that shows me I've got flaws in my data table. So I should press Control C and drag it down. Now that's what we're meant to get as far as systematic errors are concerned. We're meant to get the same result each time. So increasing the amount of mass is not meant to change this, but it will. And then you need to discuss why. And so Just doing the data table, we'll just press um, left control button, and that's our final answer. And so we insert scatter graph like that. Choose one with heaps of grid lines. I prefer that one, just there. All right. And so the mass of the food, press Control C, was over here, and the energy, which is over here. So Control C, Control V. All right. And then left mouse click on our data button, add trend line, data point, display equation, and R squared. Um, don't want this stuff here. Okay, so that is meant to be a straight line. I don't know if yours is going to go up or down or stay a straight line. Sure, we'll see what happens. And hopefully you've got this data table here ready. And just a reminder, I did skip this, which is a massive error. You could improve that. So you're going to have before after change. So you could have that here. And that'd be a massive improvement. And it'll just be like, instead of being one column, there'll be a three column here and a three column here and a three column here. Um, and then you'll get average change of mass, and it'll get much better results. Although it'll only still be like 20% instead of whatever that is, 1%. Um, okay, because that's the sort of error there is in the experiment. Okay, so I advise you to get the actually the table and graph set up before you do the experiment. But if you didn't, well, just do it after.